This is a video on slope fields, and so we'll learn what those are and what they're used for. And it basically, the idea to think about it is when you solve a differential equation, like when we've been integrating stuff, we keep writing plus c. Well, we write plus c because there's a whole family of curves that are the answers. And so the slope field is kind of an illustration that we mark some little pieces of tangent lines in order to make it look like the shape of the curves. And then there's a lot of them, and it depends on where you start and where you finish and stuff. The shapes could be a little different. There's a picture of one there on your notes at the top. That's an example of one, and so we'll learn how to draw those and then kind of what it means. All right, so for this first example, we have a differential equation, and remember that just means an equation with a derivative in it. So this says dy dx equals 3x minus 2. So what we're going to do is we're simply going to make a little table of points, and these values are going to be x and then dy dx, which of course means the slope of a tangent line. And so we're just going to pick some values. We can pick anything we want. We're just going to pick the values, though. Here on the picture, we see that x is running from -2 to 2, and so we're going to plug those in. And in this case, the only variable that I have here on the right is x. Sometimes you'll have x and y, so you'll have a more to your table, but here we only have an x. So let's plug in -2. So again, we're plugging it into dy dx. So we plug in -2, we get -2 times 3, which is -6 minus 2 is -8. I'm going to go ahead and fill all these in, and then we'll go ahead and I'll show you how to draw it on the paper or on the graph. So if we plug in -1, we're going to get -3 minus 2, that's -5. If we plug in 0 to the derivative, we get 0 minus 2, so that's -2. Plug in 1, we get 1, plug in 2, and we get 4. So what we're going to do is everywhere that x is -2, we're supposed to sketch a little tiny piece of a segment that kind of shows the tangent line, the way the slope would be when x is -2. Well, it's all the places on the vertical line through -2. So at each little crosshatch thing, I'm going to make a little tiny segment that slope looks like -8. Well, -8, of course, is super steep, so these are really pretty straight up and down. Okay, so that's what that looks like. At -1, we have the slope of -5. So still really steep, but a little bit less steep than the previous ones. So down -1, all of them are going to be slanted, still negative and still pretty steep, but not quite as steep as the others. And then at 0, all the slopes would be -2. So again, a little bit less steep, but still steep going through at 0. And there would be my little segments. And then at 1, we have a slope of 1. So 1 would be going like right through 45. So we just draw that. When x is 1, there's my little segments. And then when x is 2, we have a slope of 4, and 4 would be much more slanted. And so we're going to make much steeper, so we're going to make that. So there's a slope field. So if I look at the slope field, I can kind of see the answer. So what we're going to do, we're going to go ahead and solve this differential equation because it's super easy to solve, so that you can kind of see in this picture why it makes sense, the answer that we got. So if we were to solve this differential equation, remember we only have one way to solve it, and that is separation of variables. So we take dy and leave it alone, and we move the dx over to the other side. Then we integrate both sides. Integral of dy is y. Integrate this side, and you're going to get 3/2 x squared minus 2x plus c. Well, if you look at this picture, you can see that the solution to this differential equation is a parabola that opens up Well, if you kind of look at the segments that you've drawn on your picture, you can kind of see, hey, that looks like a parabola that opens up if I think about the tangent lines. So if you just imagine, you know, you're doing something like this, there's infinitely many of them, but you can imagine there being a parabola that kind of goes through there, okay? And we'll draw some in a little bit, but you're kind of imagining that the slopes of the tangent lines are working out that way at these points. Like this would be the slope there going through one and so on, okay? So that's the idea. So it's, remember, there's a whole family because of the plus c. There's infinitely many solutions to this problem. This is example 2. It says example 3, but it's example 2. We're going to sketch a slope field again, and then we're going to use integration to go ahead and solve it like we did on the last one, but this one actually asks us to do it. So this time our dy dx, our differential equation, is equal to 2x minus y. So we need x and y each time. So what we're going to do is we're going to fill in the points that we have on this graph. So we only have points from -2 to 2, and then we have y values from -2 to 2. So we're going to pick some of those and graph those. So if x is -2 and y is 2, so I'm going to start with that point on the upper left. I plug into the differential equation. So -2 times 2 is -4 minus 2, because I'm plugging in. So this would be 2 times -2 minus 2. So we would get -6. I hope you have the same problem. I'm looking on my paper. I think it is. All right, 2 times -2 minus 2, so again, -6. So that means at -2, 2, I need a slope of -6, which is pretty steep and in the negative direction. Then I'm going to do, let's do -2, 1. So then you would have 2 times -2, which is -4 minus 1, which is -5. So at -1, still steep, but a little bit less than that steep, or at +1, sorry, -2, 1. Then I do -2, 0, and I get -4 minus 0, so I get -4. So now it's a little bit less steep than what those are. And then I'm going to do -2, -1, and we're going to see what we get there. So we get -4 plus 1, so we get -3. So again, still negative, but a little less steep. -2, -2 would be -4 plus 2 would be -2. Of course, we can kind of see the pattern there. So again, a little bit less steep, but still negative. Okay, I just realized that this does not match your paper, so I'm actually going to, so you can just erase, this isn't a whole lot, we're going to erase and we're going to do this again because that's not the right problem, and we can't actually finish this problem if we do it that way. So the problem is supposed to be 2x minus y dy dx equals 0. So we need to solve that for dy dx in order to have something to plug into. So we're going to have minus y dy dx equals -2x. So dy dx is going to equal 2x over y. Okay, so that's what we're going to plug into now. So just erase what you had, and then we'll fix it from here, and we'll get the right graph drawn. So we'll go back to plugging in -2 again, but this time we'll plug it into the right place. So we'll go back to the point -2, 2. That's fine. That's the upper left point that's illustrated there. And so now we're going to plug in, though, to the 2x over y. So -2 times 2 is -4, divided by 2 is -2. So now when I put that graph on, that's going to be a lot less steep than what we had. So then we do -2, 1. So we plug in again, 2 times -2 is -4, divided by 1 is -4. So now it's steeper at this one. as negative 4. If I plug in negative 2, 0, that point, well, you're going to end up with negative 4 over 0, which of course is undefined. So that means that we don't have anything drawn there. So there won't be anything drawn at that point. We do negative 2, negative 1. That's going to be negative 4 divided by negative 1. It's going to give me a positive 4. So this one should look just like the one above, only slanted positive. And then we have negative 2, negative 2, which is going to give us a 2. So again, less slanted, but now in the positive direction. So we do similar things for the other points. So I'm not going to fill the whole table in. I'm just going to do the values and see what we get. Now you'll notice at the x-axis, every single time y is 0, so you're not going to have any points there. So I don't even have to try those. So let's go to negative 1, 2, which is right here, and let's plug that in. So x is negative 1, that gives me negative 2 over the y, which is 2. Negative 2 over 2 is negative 1, so that's going to be slanted just like this. Then negative 1 is the next point directly below that. Negative 1, 1, sorry, is this point right here. So plug in negative 1 for x, you get negative 2 divided by negative 1, you get negative 2. So again, a little steeper than that last one. And then again, it's undefined there. If we plug in negative 1, which is this point right here, negative 2 times negative 1 is negative 2, divided by negative 1 is positive 2. So this one is going to have a positive 2 slope. And then we plug in negative 1, negative 2. That'll be negative 2 divided by negative 2, which is 1. So we get a slope of 1 here. All right. Then let's go when x is 0. So if we're right here on the y-axis, if x is 0, then it doesn't matter about y except that we can't have 0 over 0. All of these are going to be 1. Or 0, I'm sorry. All of those are going to be 0 because the slope is going to be 0 over some number. So you're going to get 0. So all of those are going to be horizontal. Then if we start plugging in some more things, we could get the rest of the graph. I'm just going to kind of go ahead and do these really quickly. So if we do 1, 2, we would get 2 over 2, which is 1. So we want to slant right exactly like 45 degrees. If we do 1, 1, you're going to get 2 over 1, which is 2, so a little bit steeper. Again, nothing at 0. Then if we do 1, negative 1, you're going to have 2 over negative 1, which is negative 2. And then 1, negative 2 is going to be 2 over negative 2, which is negative 1. And then you're going to do similar things over here. So I'm actually not going to do that. You can plug those points in and kind of see what they look like. But that's the idea. You literally just plug points in to the slopes, to the numbers, and draw the little slopes. So if we were going to go ahead and solve this, then we would want to separate the variables. So we're going to take and write dy equals 2x over y dx. And I'm almost there, but I've got a y and an x both on the right. So I need to multiply by y on both sides in order to get it over to the other side. When we separate variables, the only way we can separate them is to multiply or divide. You cannot add or subtract. Then we integrate both sides. We get y squared over 2 equals x squared plus c. And then we want to basically solve this for y. So I'm going to multiply everything by 2. That's y squared equals x squared plus 2 times a constant, but really that's just a different constant. I'm going to put c1. You really don't have to do that, but that's a different constant than the previous one, but still constant. So if I solve this for y, then I'm going to square root both sides, and that's plus or minus the square root of 2x squared. Sorry, I multiplied everything by 2. I forgot to write the 2 there. 2x squared plus the constant. And it doesn't matter if you write plus the constant or minus the constant, because the sign of the constant will fix itself. And so we have both of those solutions there. We have square roots and plus or minus. All right. So let's go to the next question. So here we have dy dx equals minus x over y. We're going to answer dy dx for the various sets of points that are listed here and then talk about what's going on. So all of these are in 4 different quadrants. So if we pick 1, 1, and remember we're plugging into this, so we simply plug in 1, 1. So we'll have negative 1 over 1, so we get negative 1. If we plug in negative 1, 1, you'll get negative of negative 1, which is 1 over 1, so you get 1. If you do negative 1 over negative 1, you'll get negative 1, and 1 over negative 1, or 1 and negative 1, you'll get 1. And those are pretty simple. You can do that arithmetic. So what it looks like is dy dx, we can pretty much see what's going to happen. It's going to be positive if it's in quadrants. Well, if this is quadrant 1, negative 1, 1 is quadrant 2, negative 1 would be quadrant 3, and this would be quadrant 4. So it appears like it's going to be positive in 2 and 4, and that should make sense because in quadrants 2 and 4, x will be negative, and or quadrant 2, x is negative, but then that takes the opposite, and y is positive, so you'll have to get positive. When you're in quadrant 4, you're going to have the opposite, where this is a positive you're plugging in, and the bottom is negative, so it ends up negative over negative. And then you can see that it's going to be negative when we're in quadrants 1 and 3 for similar reasons. Now the advantage to that is if I'm trying to match a slope field to a solution, then this can help me. This is one of the things that can help me see that. So now let's find out what happens at all of these points. So we have 1, 0, 2, 0, negative 1, 0, negative 2, 0. So these are all x-intercepts. Well, if we do that, remember that our function is, our dy dx is minus x over y. Well, in each of these 4 points, y is 0, which means I would be dividing by 0. So we have undefined, 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 undefined. Okay, so every time. So what that tells me is if I was trying to look for a slope field to match something, I would realize, hey, all the way along the whole x-axis, there's not going to be any little slopes drawn because it's undefined. The slope is undefined there. So if you were writing a slope that was undefined, what kind of equation would you have? Well, this is on the x-axis, so you would have an equation of y equals 0. And if the slope is 0, we would have x equals 0. Would be the description of that for this differential equation. Now, look at these values. So now we're at 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. So we're at places where x and y are equal. So kind of on the diagonal there. Again, we're doing dy dx equals minus x over y. So if we do 1, 1, we'll get negative 1 over 1, which is negative 1. If we do 2, 2, we get negative 1. If we get negative 1 over negative 1, we're going to get negative 1. And if we do negative 2 over negative 2, so you have negative of negative 2 over 2, and so on, you get negative 1. So it looks like, when would we get that? Well, that would be anywhere we get negative 1, anywhere y equals x. And when would you get 1? Well, you would get 1 anytime y would happen to be the opposite of x. That's when I should end up with a 1, because there's already a negative in the problem. So this is, again, just for this differential equation. So we're going to sketch the slope field using the values that we did, and then we're going to sketch an actual a solution. So I'm going to use red so it shows up better. Probably should have used red on the last one, but we're going to just draw in the points, some of the points that we found. So for example, we found that at 1, 1, we had a slope of negative 1. So we can draw that in. At negative 1, 1, we had a slope of 1. And at negative 1, negative 1, we had negative 1. And here we had, again, positive 1. So there's some slopes I can draw in. If we're at 0, 1, so x is 0, well, anywhere x is 0, then this whole thing was going to be 0, except we can't have 0, 0, because we'd be dividing by 0. So we have all of those points. We know that it's undefined all the way along the x-axis, and then we could just keep drawing in the other points that we got. So for C, we got 1, 1 was negative 1. I've already done that one. 2, 2 was also negative 1. And really that means all of these are negative 1. They're all the same when you have x and y equal to each other. And you can kind of see that, hey, when x and y are opposites, then we're going to get positive 1 for the slope. So we've really filled in quite a bit here. So let's just fill in a couple more values so that we end up with a little bit more in our slope field. When you do a slope field on the AP test, it's normally only about 6 or 9 at the very, very most that you have to fill in. You don't have to do very many of them. But I'm going to go ahead and fill in a couple more so we can sort of figure this out. So let's go to 1, 2, remembering that it's minus x over y. So if I plug in 1 for x and 2 for y, I get negative 1/2. So at 1, 2, I'm going to have a slope that is pretty flat. And so you can kind of figure out at 1, 3, you're going to have even flatter, but negative, because you're going to have negative 1/3. And then if we plug in 2, 1, so if x is 2, we get negative 2, y is 1, so we get a slope of negative 2. So it's actually a little steeper. If we do 2, negative 1, we're going to have negative 2 over negative 1, so we'll have positive 2. So you can again kind of see what's going on there. We can sort of just figure out, you can plug values in if you need some practice on arithmetic, then definitely do that. So we can kind of see what's going on here though. You're going to get sort of the same kind of thing on this side, just turned a little bit. And then that's all I'm going to plug in. You could do more, and you could certainly fill in more. All you're doing is a bunch of arithmetic. Now, the difference in this question, it says, let's draw the particular solution that passes through the point 0, 2. So we have to go through this point, and so we know that we have to be this way because we have a tangent line that is horizontal there. And then you're just kind of looking. When you draw these solutions, generally do not draw them in such a way that you end up going through where any of the tangent lines actually are. You kind of just follow along them. So you just imagine if this curve is going along, I can kind of see how I would get, and I can see the symmetry in the solution, so I can kind of tell that too. I can kind of see that I would get a curve like this. You can sort of visualize how all of those little segments I've drawn would be tangent to that solution. So that's basically how we do that. Now, if I want to know the solution to that curve, I could go through the process and solve it, and I think we'll do that. So I have dy equals minus x over y dx. Now I got to get the y over here again. So I have y dy equals minus x dx. Separating the variables, integrate both sides. So I get y squared over 2 equals minus x squared over 2 plus some constant. Well, let's look and see here. Sometimes we need to pay attention to realize, hey, this is actually an equation that I know. If I move the x squared over 2 over to the other side equals a constant, multiply everything by 2, you can see that you get x squared plus y squared equals 2 times some constant. Well, looking at this curve, we know that we have 0, 2 was one of the points on the curve. So if we plug that in, we can actually solve for what that constant is on the right. So I can plug in 0 for x, 2 for y. That gives me 4 equals 2 times c, which means I'm going to get, I'm going to solve that. I'm going to get c is 2. So I'm going to end up with x squared plus y squared equals 4. And we'll do more solving later, but that's a start at that. All right, so what happens as we moved to the left and right with a fixed y value if we're looking at this curve? So as we went to left and right on this curve and we had the y value fixed, in other words, you're on one of these, you want to be on one of these horizontal lines. What was happening as you went left to right? Well, the slope was positive and really steep, and then it was stayed positive but got less as I went until it became 0 here in the middle, and then it was a negative slope, and then it was a steeper negative slope, and then more negative. That's what was happening. So what's happening as I go from left to right with a fixed y value, it is that as x increases, so as I'm going to the right from the left, as x increases, we see that dy dx was decreasing because we went from positive, high values positive, down to 0, and then to negative, and then bigger and bigger and bigger negative. So it's getting smaller. So if we go up the x-axis with a fixed value, so if we were just going, thinking about this, say this vertical line right here, what is happening? Well, as y increases, we see that as we go, we are getting flatter and flatter and flatter until it's approaching 0. It's flattening out. So as y increases, we see that dy dx actually approaches 0. It's getting flatter. So it's getting closer and closer to 0. All right. So here's a big thing that you need to be able to do, and that is match. So when we're trying to match them, we're going to go ahead and talk about some things, and then we'll write them on a little chart on the back to think about what fits. So when I'm looking and I'm trying to match up graphs, I'm going to look for the shape that sort of looks like the shape that's the answer. Okay, so for example, if we look at, well, there's a whole bunch of things we can look at. So let's like, for example, look at E, okay, to try to see what we can match. So if we look at E, you notice that when you're at 1, you get a slope that is 0, and that there is nothing, there are no y's that are negative. So if we look at all of our choices here on all of our equations, all 8 of them, we don't have any issues with y being negative except for right here, because we're not allowed to put negatives into ln's. And it sort of makes sense when you plug in 1, when you do ln of 1, when y is 1 right here, we're going to definitely get a slope of 0 because ln of 1 is 0. So that matches 5 with E. And we can do similar things in order to figure these out. So you can also just sort of look at the shape. So like, let's look at H for a second. So if you look at H, you should certainly recognize that looks very much like a trig function. You can imagine the solutions to this being just going up and down like this. You can sort of see that graph, that shape there. Well, the only one that's just a trig function with only one variable, cosine x, is 4. So I think that 4 goes with H because you can see that. So let's look at D. I always look at things that have unusual characteristics and see if I can figure something out. So on D, we don't have any values over here. So we have an issue with the domain. So we're not allowed to have x values that are less than a certain value. So if we look at all of our choices here for things that x has a problem with, it would be number 1, and that's a square root. We cannot have negatives underneath square roots, and so that fits for D there. Let's look at some other choices here. So let's look at B. So on B, we can see that we have right here, if you're going on the x-axis, you can see that we have slopes of 0 all the way down the whole x-axis. We also have that on A, so we need to keep that in mind. A also has 0 when you have x equals 0. So both of those would be ones that I'm going to go look and see first if I can figure that out. So when would x equals 0 give me an answer of 0? Well, that would be here, because if x is 0, you'll have 0 times something, which will be 0. And the other place you would get 0 is here. So that means that A and B have to be 2 and 7, have to fit those values. So all I have to do is pick something and sort of see which one could kind of fit that. So if I look at number 7, I have minus x times y is what's going to give me the slope. If I look at this graph right here, I can see that as x gets, for example, more negative, as I'm heading this way, x is more negative, and then y gets bigger, I'm definitely getting bigger numbers. Well, that makes sense for number 7, because that is totally what would happen as x gets more negative. So like say you have negative of -5 times a y value like 4, you're definitely going to get a really, really, really steep line. So I think that number 7 is going to fit B, which means that number 2 must be A, because of the, again, you have 0 slopes here. So those are the kinds of things that you're going to look at in order to figure out what's going on, and then start matching, and then you kind of eliminate, and what's left is left. So if we look at, let's look at C. So C has lots and lots and lots of super, super steep slopes for the values of y. Well, if you look at 6 here, you can see that if you plug in stuff to y, you're going to square it and then add 1, and that's going to be your slope, which is going to be really, really, really steep. So definitely 6 will go with C. And then let's see, what do we have left? We haven't matched F or G. And both of the functions that we have left have to do with sine and cosine. And that kind of makes sense. F and G look sort of curvy if you're looking at the shapes there. And so if we look at G, the difference in the equation is you're going to take sine of the y value, and then you're going to add the x that you're at. And on number 8, you do cosine of, and you add the x and the y's together. So that's going to change things greatly, because as x and y get bigger, you're going to take cosine of bigger and bigger numbers, but remember, it's periodic. It's going to keep repeating. So I think that's going to make me fit F here, because as I keep getting bigger, I get slopes that start to repeat kind of and curve around, which means that G must go here with number 3. Now, these are difficult ones to match, so I'll tell you that just kind of look over that and see why they sort of match up, kind of think about the points that you would plug in. But that is something that's good to be able to do. All right. So on this example, it says here we're given a differential equation, we're given a point, and we're given the slope field. We're going to use the slope field to sketch a particular solution through the point, then use integration to find that particular solution. So the point that's given is 0, 1. So this is the point given, and I want to sketch a solution that goes through 0, 1. Well, if you look, you can see, you should be able to really see here this little asymptote idea, because you can see how the tangent line slopes are kind of slanting that way. So we can definitely kind of see that. And if you just sort of, like I said, don't necessarily draw on the lines, just draw near the lines, and you can see how this is kind of a reasonable graph here that's going to give me those slopes. And as I go this way, it's going to flatten out more, and you can see it fitting those slopes. So that, to me, looks like about the right solution that you would have there. So let's see what happens if we separate the variables. So we're going to have dy equals 1 over x plus 2 dx. So we integrate both sides. So we get y equals, remember the plus c just needs to be on one side, not both. We get ln of absolute value of x plus 2 and then plus c. So we want to find c. Well, we're always going to plug in to find c right away, which again, we're going to do another section where we separate variables and solve a lot more. This is not as in-depth as we're going to get. But if I plug in 0, 1, so I plug in 1 for y, and I plug in 0 for x, I can solve here for c. I get that 1 minus ln of 2 is going to equal c. And that's just what it's going to be. So that means that the function that I'm actually looking for is going to be y equals ln of absolute value of x plus 2 and then plus the constant, which is 1 minus ln of 2. And that's the actual solution that you have. All right. So some different strategies that you can do if you're trying to match slope fields. So one thing to notice is if dy dx has x only, okay, so as x only, slopes change left to right only. Okay, they're only going to change as you go left to right. If dy dx has y only, then it's going to be the same thing. The slopes are going to change here we need to change them. Slopes needs to change up and down only. So as you go across, they're all going to be the same slopes. It's just up and down they're going to change. If you have dy dx has an x plus y, or x and y, sorry, then the slopes change in both directions. Okay, so if you have both, you're going to know, hey, they're not following a vertical or horizontal line where they're staying the same, so there's an x and a y. I'm not going to see that. Then my biggest thing that I always try is I look for places where dy dx equals 0. I look for where dy dx would be undefined. And then honestly, I usually go from the graph to the equation. So on the graph, I'm going to look for, maybe just look for patterns of slopes that are like look to be 1, so slopes that are 0, or look to be 1, things like that. So you're going to look for that and see if maybe diagonally all the slopes are 1s, or maybe diagonally they're all 0s. But if I look through that, then I can kind of see a pattern there and then match up which equation would have that happen if you're at those points. So there's a lot of practice really is the best way to figure everything out. So really that's what you need to do, is just spend a lot of time practicing by plugging in stuff and looking at the slopes and then kind of analyzing the graphs, and that's how you'll get more familiar with them. So we'll do some more with separating variables and things in class, but this will give you enough to get by and understand a little bit about slope field.